Okay, so now I'm to the last part of this talk, which is about the pitches that we've developed at Utah State University. As I've mentioned, we cannot project pitches with gyro. So, in order to demonstrate that seam shifted wake effects exist, we've had to develop a couple pitches that don't involve gyro. And it turns out that this is absolutely doable. Um, the They still require a specific seam orientation. They will work on any efficient pitch, whether it's in the three that I'm thinking about, or a fastball, a curveball, or a changeup. And I think that these are relatively easy to understand and to throw. You can teach somebody how to do it pretty quickly, at least on the definitely on the fastball. I think on the changeup too, and I've seen some evidence that a curve can be done. So I want to start off by talking about what we call a looper. The reason we call it well, first of all, what I'm trying to show here is a 3 o'clock tilt changeup pitch. It's moving to the left, and if you view it from above, it's going to look like this. So the reason I call it a looper is that the pole of this ball is right around there, and I have a seam looping around it. And from what you've seen, you should understand by now that if I have a seam in that region, whether it's on the front or the back of whether the seam is in front of it or in back of it, it's going to cause separation on that side, and that's going to tilt the wake and push this ball down. From the side, it would look like this. That loop is up here at the top. I could just as easily flip the ball over with the same axis, and then it would have the opposite effect of what we're going to show here. So I'll get to the scuffball a little later on. Let's focus on this one for now. And if you're real if you're very clever here, you might notice that this looks a bit like the Laminar Express or the disco ball changeup, except for that the orientation is just slightly different. The region that's going to be affected by that seam, I think, is a little smaller than it would be for a Laminar Express, and that's the main difference. So we tested this pitch using the same cannon, but instead of taking PIV data on it now in our little box, we're going to fire it across the room. We shoot the ball 55 feet from about 6 feet high. We use the same cannon. We are in a, like I said, a straight up and down axis, so 3 o'clock tilt. At home plate, we have a camera, a high-speed camera that can view the ball crossing the plate. And over here, we have a Rapsodo 1.0. I don't talk to too many people that use Rapsodo 1.0 anymore. Rapsodo offers a pretty desirable upgrade to their 2.0, and their 2.0 system is generally better, as you would hope. But it turns out that for this study, I think the 1.0 is exactly what we need. And the reason for that is that 1.0 sits behind home plate and tells you where the ball went without any model. So if you here's a video of this test being done. The Rapsodo is sitting right here. It's looking right at home plate. And the cannon has the tip horizontal. That's what gives us that 3 o'clock spin. I have a bunch of metrics over here on the right-hand side. About 90 miles an hour, between 1100 and 1200 RPM. It says 99% efficiency. I know it's 100 because that's all we can do. About 15 inches of horizontal break, about 0 of vertical break according to the Rapsodo, and pretty close to a 3 o'clock axis. So ball's traveling 55 feet, and the Rapsodo is going to give us information like shown here about where the ball went. Now, one thing I want you to notice, I apologize for the fact that the video speeds up right at the end. This is a feature that's built into the video on Rapsodo, and it makes a whole heck of a lot more sense if you have somebody winding up and throwing the ball than if you have this machine suddenly throwing the ball. But try to filter that out, that the ball seemingly accelerates suddenly at the end. And I want you to think about whether or not this pitch looks unusual. Do you see anything happening here that's surprising? You can see the break to the right, it's pretty clear, and the ball drops like you would expect the changeup to drop. So this is with the loop on the top. And I'm going to switch now to a case with a loop on the bottom. Here's the loop on the bottom. And again, I would ask you the same question. Does the travel of the ball look super unusual? If you were the catcher or the pitcher, would you say, oh, holy cow, something really happened there? And my belief is that you would not. And the reason is that I'm going to show you in a minute, we're adding 5-8 inches of break to something that's already giving you 15, and that's tends to be rather subtle. Again, I want to point out all these metrics. They're essentially the same as the first pitch I showed you. Now, if I flip back to that, I would ask you to focus your eyes down here, and you can see that these two pitches have very different locations that they arrive. Rapsodo still puts their horizontal and vertical break essentially the same, and that's because Rapsodo computes break based on a Magnus model. That's all it can do. And so that break has nothing to do with where the ball ended up. It is purely a function of the spin and the axis of the ball. That's where they compute the break from. Okay, so if I overlay the last two frames of these two videos, there's the first ball, there's the second ball. You can see the difference in their location. And that's also exactly what's shown here. After working with this for a few months, I'm very happy that Rapsodo does tell us, I think, very accurately where the ball went. And it makes it a great tool for investigating these things. So, okay, so here is the results of all the shots we took. The open symbols are individual pitches. The big dots are the average of all those pitches. So the black dot here is a straight two-seam 3 o'clock axis. So in that case, I just fed the ball in there in a way that I don't think will generate any seam effects, and fired it 5 times. This is the average of that. We take that break, which was about 15 inches, and we subtract it from all the other results. So that's what I mean by saying that Magnus is removed from all these results. The results here are what is happening aside from Magnus. And so now focusing on the red and the blue dot, those are essentially, the red dot is when I put the loop on the bottom, and the blue dot is when I put the loop on the top. If I put the loop on the top, it pushes the ball down. If I put the loop on the bottom, it pushes the ball up. We expected that, and we were happy to get about 4 inches plus and minus compared to what the baseline case did here. What was surprising to us, and we still don't fully understand, is that the ball also moves about 2.5, 3 inches to the right in the case of the loop on the bottom, and about the same amount or maybe a little bit more to the left when the loop's on the top. So you put those two together and you're talking about more than 5 inches of break total just from this orientation. This has nothing to do with Magnus. And in fact, I would point out that we're adding to Magnus in this case and we're subtracting from Magnus in that case, which makes it look to a scientist like a linear effect. We can add this loop effect to the Magnus effect, which is very attractive. Now there's 2 other data points there, the orange and the green. Those are the same orientations, but for a ball that had a smaller seam. These are 2019 baseballs. They generally have small seams, but the red and the green results were from a ball that's about 20% lower seam than the red and the blue. So the seam height seems to matter, which is not terribly surprising. It's a rather encouraging result because the 2019 balls kind of had bad seams, in my opinion. They were rather degenerate, and which caused the low drag and all the home runs and all that. They're also going to make it less attractive to throw these kind of pitches. I don't think we'll ever see those kind of seams again, I hope. And so I believe that everything I'm showing here will only be better with a baseball that we're likely to see the next time that Rawlings puts them out. So like it says on the slide, all 3 of these pitches have the same tilt, RPM, and speed, which according to everything we've thought about up till now says they should all go to the same place, and obviously they don't. So this is high-speed video acquired from the side. This camera's sitting right at home plate, watching these 2 balls go by. It looks like the bottom one's moving faster than the top one, and that's because the bottom one has moved towards the camera, and the top one has moved away from the camera. But this is just to show what they look like going by, and you can see that I do have the orientations that I was aiming at there. Okay, I mentioned a scuffball. This was, we did a test where we actually physically scuffed the ball and realized that you can get a lot of break that way, which is not news to anyone. We decided that kind of inspired us to say, hey, can we make the ball look like it has a scuff on it? And we thought to do that by putting the seam right on the pole of the ball, so it's going to be spinning right around that. This is before we did the looper test, and really this amounts to a smaller loop, or an almost zero size loop, and I think it's basically affecting a smaller part of the baseball than the looper does. But I'm including it here because when we did this test, we did it as a fastball rather than a changeup. So this axis is straight horizontal, and we got a very similar result. You can see that our baseline is here. If we put the scuff on the left side, it moves to the right and down. For reasons we don't understand, when we put it on the other side, we didn't get this symmetric effect. And this may be because this is less effective. It may be because we misaligned it a little bit. And it also could be that somehow what's happening with the looper on the changeup pitch is dependent on the fact that the ball is going to drop a bit. And the axis relative to the direction that this ball drops is different than the other one. So that's really all I want to say about the Scuffball. But this is our only fastball test. And we see a lot of the same features, but not all of them that we're getting with the looper. I'd like to repeat this with the looper orientation, obviously. Probably the next thing we do. So what if we wanted to do a looper fastball? Well, we did it with a 3 o'clock tilt, which is straight sideways movement. The loop on the bottom moved the ball up and to the right. And so if we shift that to 130 tilt, if I just rotate that a little bit counterclockwise, and that's the common right-hand pitcher fastball, then the break would be straight upward. It would give you 5 inches more than your current fastball, and that is totally independent of RPM, which I think is really exciting. So this could turn everybody into Mike Minor, who I just learned today has the best fastball RPM. In fact, I think it can make you better than Mike Minor because as your RPM get up into the 2,500 range, you really can't add a lot more Magnus effect from there. Even if you, in fact, 5 inches on top of a 2,200 RPM ball would require, I think, 3,600 RPM or 3,800 RPM to get that much vertical break. So to me, this is really exciting. You can have a ball that arrives at a much lower approach angle than what you can do simply by spinning the ball. You could also get drop if you just simply turn the ball over. So some disclaimers about all this data. These are all 2019 baseballs. They're fresh baseballs, so none of this has anything to do with scuffs or damage to the balls. We did all the testing at 90 miles per hour and relatively low RPM. There's no humans involved, so we can repeat the pitch over and over again, which is really convenient. The orientation relative to gravity may matter. And what I mean by that is that this may be different for a fastball or a curve than it is for a changeup, and we don't know the answer to that yet. I am really confident, going back to the looper, I am very confident, let me just go back to that plot, that this vertical is totally independent of orientation and of the axis of the ball and of RPM. This horizontal probably is not. I think when we go to very high RPMs, we might get less horizontal movement from this effect. And when I say vertical and horizontal, I'm talking relative to 3 o'clock. If we turn that to 12 o'clock, those two switch. Okay, back to my disclaimers, okay. Okay, so what I am really proposing to do is to nail out, to knock out these questions. And I get these every time I give this presentation. Somebody asks me, what if you do it at a different speed? How accurate does the orientation need to be? What if your gyro degree isn't quite what you wanted it to be? Does the axis matter? Does it matter if it's a changeup or a fastball? And we frankly don't know the answers to these questions. We have exactly what we need in order to determine the answers to those questions. But that's going to require, I think, about another year of work. The other major issue is detection. If you throw this thing, how do you know that it happened? I'm going to show you later on in this presentation, a couple of videos down, how you can detect that you threw the ball correctly. But once you are convinced that you threw the ball correctly, convincing yourself that something happened is still a challenge. Like I said, maybe you got 15, 20 inches of break and you're trying to add 5. That might not jump out at you. And unfortunately, Rapsodo and TrackMan aren't really well suited currently to tell you that this is going on. I think they might give you some hints, and I think maybe together they can actually make it clear what happened, but they're not built to handle this currently. So my claim is the effects are important 5 inches of vertical break is great, but it might be subtle enough that you can't see it with your eye. It's easy to detect in our lab because our picture is very consistent. It's going to be harder for you to detect in the field. So I think that's another area that requires some research. So in conclusion, seams cause the wake to form early on one side, on the side that they are on. If you can have that on one side and not the other, that makes a force on the ball. If you can maintain that, the ball will break as a result. 4 known pitches that use this that I've seen. Gyro pitches are the laminar express two-seamer and a disco ball changeup. The efficient pitches that we're working on is a scuffball or a looper. And that's really it. I believe there's more. Baseballs are something else. Every day I think of someone suggests to me, or I think of another way to do this. I think we've just scratched the surface. So to me, it's very, very exciting. So I just wanted to thank you and note that I have a website where all this is. In addition to, there's several other people I wanted to thank, and I appreciate it if you hang out one more minute and listen. Daniel Hudson was the guy, the undergrad, that originally started working on our setup. Didn't get to ever see it run, but Nazmus Sakib picked it up after that and did an excellent job of the initial data that we took on high school baseballs. Andrew Smith is the grad student that's done most of the work so far. He's a master's student, is about to graduate, and is very keen to find a job, especially in baseball. So the guy that's going to take over from him, hopefully, if we can fund another year of work, is John Garrett, and he did the scuffball tests that I presented to you. I also wanted to thank, from the bottom of my heart, Rob Friedman, the pitching ninja. Nobody would know who I am, I don't think, if it wasn't for him. And I appreciate him, his constant support. Trip Summers has also been really helpful talking about this stuff. And probably most of all, the rather obvious person I should thank is Professor Lloyd Smith at Washington State University, who funded Andrew for this entire year and has really made all of this possible. So I don't think he gets enough credit for this. And I hope more people know that he stepped up and paid for this full year of work. So thank you to Lloyd. And thank you for listening.